Okay, we're looking at elementary functions, and we're going to look a little more in detail at power functions, at least a more detailed introduction to power functions, probably along lines that are pretty non-traditional. Okay, later on, and soon actually, we'll look at exponential and quadratic functions. Okay, a power function is of the form y equals x to the p. We'll say y then is your function f of x equals x to the p, or rather your function is f of x equals x to the p, and we're going to let y equal the value of that function. Now usually the first thing you do when you have power function, when you're introduced to power functions, is you start plugging in numbers for x and construct a graph and so forth. And that's not a bad thing to do, but I assume you've already done that. And that actually is pretty misleading, because I see people at the end of a pre-calculus course still wanting to graph everything by making a table and plugging in points. And that's completely counter to what you need to learn to do and the way you need to learn to understand functions. And as long as you lean on that crutch and on the graphing calculator crutch, you're never going to understand functions as well as you need to. So we're not going to do any calculations here. No calculations whatsoever on this whole page. Okay? Now, here's a claim. This is a claim. It's not proven. Okay? We will prove it. But it's actually to prove this thing in all its equivalences and so forth is actually a little bit difficult. One part of the proof is easy, and another part is just pretty challenging to understand even what it's talking about. Okay, well, that's okay. Okay, I'm not going to ask you to do the hard proof, but the easy proof you should be able to do without too much trouble. So we claim, but we haven't proven, that whenever you have a power function, doubling the value of x always changes y by the same factor for any given power function. Okay, now this is actually easy to prove. The harder thing to prove is that if doubling x always changes y by the same factor, then what you have is a power function. It's a completely different statement. It's a converse of this statement, essentially, and very much more subtle to prove that one. Okay, so we construct this graph, and if you want to see the details, look at the longer videos. But we simply construct a graph of y equals x to the p, where the factor is 1.5. Now, this is the factor we're talking about here. Y is going to change by a factor of 1.5 every time x doubles. So we first line off our x-axis. Now you can ignore the stuff in green for now. That comes later. The stuff in white and then the stuff in orange come in order. Okay, in white we have the axes, and we've chosen some starting x value here, some point on the x-axis pretty close to the origin. And then we find the x that doubles that value, so that point is twice as far from the origin. Then a point that's twice as far as this one from the origin, a point that's twice as far as that one, and a point that's twice as far as that one. Now, if we try to go twice as far as this, we get past the end of our arrow. Of course, we could extend our x-axis. We'd be here, and then when we double that, we'd be here, and then when we double that, we'd be out near the end of the board, and pretty soon we'd be out in the parking lot. Okay, so we have a series of x values that double. Now what? Well, we got to pick a y value to go with our smallest x value. Okay, so there's our y value. Now we could pick a y value that goes with our largest x value. We could do that, and we could work backwards. But right now we're just going to pick a y value that starts with our smallest x value here. And we just put a point on the graph. Then we go to the doubled x value, and we increase our value of y by 0.5, by 50%. In other words, we make the y value here 50% bigger than here, or 1.5 times. This y value is 1.5 times this y value. And then we continue doing that. Next x value, 1.5 times this. The next y value, for the next x value, the new y value will be 1.5 times the previous. And then new x value, the new y value, 1.5 times the previous. And we get a series of points, which we then connect with a smooth curve. We also ask what happens if we continue moving closer and closer to the origin. We don't have room to slide in those points because the chalk line is too thick. Okay? But if we went twice as close, then let's see, since we're increasing the y value, or since the y value changes by factor 1.5, when we move in this direction, the y value will change by the reciprocal factor, which is 2/3. 1.5 is 3/2, reciprocal of that is 2/3. You should understand that immediately. If not, you should think about it, just by way of understanding what fractions and reciprocals and so forth are telling you about this situation. So if we were to start it out here, then this point is 2/3 the y value of this one, because this one is 3/2 the y value of this one. Okay? Well, our next point in here will be the x value will be half as great, the y value will be 2/3 as great. Well, we can continue doing that, keep going twice as far, twice as close to the origin in the x direction, with y values going 2/3 of the way, 2/3 as far from the origin. Okay? It's very clear that the x's are going to approach 0 and the y's are going to approach 0, so it makes sense to extend this process to say that the point 0, 0 is also part of this graph. So now we have a graph, and this is the graph of the y equals x to the p power function. We don't know what p is, but now the y factor is 1.5. So we can say this is a graph of y equals x to the p. Well, I'm getting ahead of myself. Let's go down here. Okay, in purple I've written things that need to be proven. Okay? Here I say the factor on this graph is 2 to the p. Okay, if p is the power, the x to the p power, then the y factor is 2 to the p. And maybe I should extend that to say that the y factor, but the only factor we've talked about or used the word factor with is this factor. That's the y factor. And it doesn't really hurt to call that the y factor, so let me just do that. Okay, so the y factor is 2 to the p. Can you prove that? That is, whatever the power of p is, 2 to the p has to equal 1.5. Okay, and this is the y factor that corresponds to doubling x. Okay, the next question, the next thing that comes immediately from this is that p is the log to the base 2 of that factor. So if the y factor is 1.5, p is the log to the base 2 of that factor. Now you might or might not have covered logs by this point, and if you haven't, then that's not going to mean too much to you, but when you do, it will. And also, by the rules of logarithms, that's easily calculated as log of the factor divided by log 2. You have a log button on your calculator, so you could actually calculate this. You could actually figure out what the power p is if the y factor is 1.5. Okay. Another thing. I'll say here, if the factor is bigger than 1, if this factor is any number bigger than 1, then as x approaches 0, y must also approach 0. Now, I just talked about how as you keep cutting x in half, the y's are cut. The y's change by factor 2/3, which makes them move closer and closer to 0. That's certainly true for this factor. I'm saying that's true for any factor greater than 1. Also, if the factor is less than 1, then as x approaches 0, y must approach infinity. Okay, I'll leave that statement up there. You might not be equipped at this point to think about that statement, but it's a fairly profound statement, not too difficult to prove. This isn't too difficult to prove. Once you understand what it means, this isn't too difficult to prove. But at this stage, you probably haven't done a lot of proof, and there's a hump you got to get over in order to do proofs. And I'll try to ease you in to that whole idea. Okay. Now here's our factor 1.5 graph again. And I've noted, I noted over here that now in green that this is now a graph of y equals x to the p, where p is log of 1.5 divided by log of 2. That follows from what we say here, whether you understand it completely or not. You can accept it. You can calculate the value of p, as I've said. Okay, the other thing we can do, and I know I was over here and I'm back over here a minute because I forgot to talk about this. We can label this graph now. Okay, we can label the graph any way we want to. This graph had no scale. All we had was a mark doubling, 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 and a bunch of marks here. There were no numbers involved. Now we can get numbers involved. And now what I want to do is I want to label a point and call it 1, 1. Okay, so I pick any point. Now x is 1, y is 1 at that point. It doesn't have to be this point. You could let this point be 1, 1. You could let this point be 1, 1. But I've labeled a point 1, 1. A little arrow there. Okay, so if this is the point 1, 1, then of course we know that matches the graph of y equals x to the p. Why? Because 1 to any power is what? 1. Okay, no matter how many times you multiply 1, you still get 1. And that even goes for fractional multiplications. Multiply 1 by itself 1.7 times. Well, that's another discussion. Okay, so having declared that this is the point 1, 1, we can now label the x, we can mark the x point for 2. And again, you could do this with compass and straight edge. Now the next thing you can't do with compass and straight edge. Okay, but here's 2. Okay, now when x equals 2, what's the value of y? Well, we go up to the graph, we go over, and what's that? Well, if x is 2, that's 2 to the p. So this point has coordinate 2 to the p. So we could calculate the value of 2 to whatever power goes with y factor 1.5. We couldn't calculate, I'm sorry, we could estimate that value. We can't construct that because it's an irrational number, but we can estimate it. Okay, well, again, here we have the same situation, but now I want to label a point, any point on the graph, and I'm going to call it 1, 5. Okay, now we no longer have the graph of y equals just x to the p. We have the graph of y equals 5x to the p. Because why? Because if x is 1, 1 to the p is 1, so y has to equal 5. So if this is, if the point 1, 5 is on this graph, then there's no choice. This is the graph of y equals 5x to the p, as best we can construct it. Naturally, we aren't going to construct it perfectly. So, again, p is log 1.5 divided by log 2. So what I ask you to do is prove that if 1, 5 is on this curve, then y equals 5x to the p, where p is log of 1.5 over log of 2. Now, that's not written very well, but that's all it says. Okay, and we've already declared that p is a log of 1.5 over the log of 2. Okay, then I ask you to construct your own graph, factor 1.5, and do something like what we've done up here, except label it to represent 4x to the p. No calculations here. No calculations. This is all just numbers and estimates. Then estimate f of 2, f of 3 minus f of 2, and estimate the solutions to the equations f of x equals 1, f of x equals 10. Estimate f of 8 divided by f of 2. Do all that with no calculations. Not very difficult. You should work on that. But of course, if you don't get anywhere, we'll give you some feedback very shortly.